Welcome to this number theory primer. In this lecture, we'll look at the notion of the greatest common divisor and let us recall some relevant things. So, we have seen the notion of division. If we have a non-zero integer and some integer b, we say that a divides b if, a divides b if there exists some integer n such that b equals a n. So that's the definition of division, and this is the notation. So when we write this, we just read it as a divides b. And there are multiple synonyms of it. If a divides b, we also say a is a factor of b, or b is a multiple of a. There may be more. Anyway, so we also saw this division with remainder theorem, which says, or at least the way I stated it was that if we have two positive integers, then there exist unique integers q and r such that you can write b as divisor into quotient plus remainder, where the remainder is in this range. It's a very natural theorem, and we gave a rigorous proof of it. In fact, we gave two proofs. Here are two problems. They generalize the division with remainder theorem as I stated it. This is perhaps the most general way to state it. Here, the divisor itself can be some arbitrary integer, non-zero, of course. If you're dividing, it better be non-zero. So, but these are like easy corollaries of the division with remainder theorem, the way I stated it. All right. So now we want to get into the notion of the greatest common divisor. So fix two integers, not both of them are 0. So this is important, not both 0. And we say that some integer d is the greatest common, some integer d is a common divisor of a and b if, there's a common divisor of a and b if, first of all, this has to be non-zero. So when we talk about divisors, it's always non-zero. So a non-zero integer d is called a common divisor of a and b if it divides both of them. As simple as that, true to the phraseology, common divisor, divisor of both. All right. And the greatest common divisor of a and b is, we write it as GCD a comma b and define it as the maximum of all the divisors, or let me just, for simplicity, maximum of all those positive integers which are common divisors. I could have just written integers here and that wouldn't change anything. But anyway. So when I say max, I need to justify that this is a bounded thing. And that's simple because if you have something, let's say d divides both a and b, then the size of d, meaning the cardinality of d, which is same as d because I'm taking positive things, the size of d cannot be more than the size of a or the size of b. So this is at most the size of either of a or b. So this is a bounded set is all I'm trying to say. This is not some infinite set, and therefore the maximum exists. Also, this is a non-empty set because 1 is clearly present here. 1 divides everything, so this is a non-empty set, and hence taking maximum is legitimate. So maybe let's take two examples. What about this thing? We have two numbers, 14 and 21. So what are the common divisors? The common divisors are so this is equal to max of the common divisors. And what are the common divisors? So 1 is a common divisor, 2 is not, 3 is not, 4, 5, 6, 7 is a common divisor, and 8, 9, 10, and you won't find any other common divisors actually. So it's just this much, and therefore this is equal to 7. So 7 is the greatest common divisor. So I forgot to emphasize that this is also true to the terminology. It's just the greatest among all common divisors. That's the definition of GCD. All right, so GCD of 14 and 21 is 7 because 7 is the greatest common divisor. And let's see another example. What about GCD of 7 and 11? If you think about it, you'll find that this is equal to 1. So it's perfectly possible for two things to not have any non-trivial common divisors. And that is something which we will study separately later. But for this lecture, we are just happy with this example. Let me just mention one more example. GCD of something like maybe 18 comma 0. What is that? This is equal to 18 because 18 divides 18 and 18 also divides 0. And of course, you cannot have anything bigger than 18 dividing 18. So that's another example. One of these things can be 0. Okay, here are some more sort of abstract examples. Note that if you have any positive integer, then the GCD of n and n plus 1 is 1. So if you take two consecutive positive integers, their GCD is going to be equal to 1. The reason is very simple. If d divides n and d divides n plus 1, then d also divides their difference. D divides n plus 1 minus n. Right? If you have something which divides two integers, then that something also divides the difference of the two integers. That's a very simple thing. So d divides this, but what is this? This is equal to 1. So this implies that d divides 1. And therefore, the only possible common divisor is either 1 or minus 1, and hence the greatest common divisor, or the only positive common divisor, is 1, and hence this holds. So if you take two consecutive integers, the GCD is simply 1. Okay, and this is what I commented earlier, that if you have two integers a and b, and again not both 0, then only then this is defined. So then GCD is at most the size of either of the participants. So that's something I already said, and it's of course not anything very complicated. And this is another very simple comment, that signs don't matter when you are talking about division. D divides something if and only if D divides the additive inverse of that. So common divisors of a and b is exactly the same as the common divisors of minus a and minus b, and so on, and hence all the GCDs are exactly the same. And that's it. So these are some simple comments that I want to make. And here is a most important fact about GCDs, or at least a most important fact, although very simple. So suppose we have two integers, which again not both 0. This I cannot emphasize enough, not both 0. And suppose a is equal to bq plus r for some integers q and r, and I'm not trying to insist that r is in a certain range or anything. I'm not saying that you get this after applying division with remainder, although you may very well get it after applying division with remainder, but I'm not trying to insist on it. I'm just saying that suppose you find integers q and r such that this equation is satisfied. R could very well be bigger than a for all I care, or bigger than b, or anything. That's completely fine. So then the conclusion is, under that hypothesis, that GCD of a comma b is equal to GCD of b comma r. So how is this useful? So suppose you wanted to find GCD of a comma b, then you apply division with the remainder. Then what you will see is that r is less than, the size of r is less than the size of b, and hence you've sort of reduced your computation space, and that is how this is useful. But anyway, right now we don't care about any division with the remainder thing or anything. We'll just prove it separately. So here is the proof. Let D be a common divisor, be a divisor of. So yeah, maybe we will develop this notation. So let's say D is equal to, or capital D is equal to the GCD of a comma b, and let's say D prime is equal to GCD b comma r. We want to show that D is equal to D prime. All right. So let D be a common divisor. Common divisor of a and b. Then D also divides R. And the reason is very simple. R is equal to a minus bq. And if D divides both a and b, then it also divides this difference, and hence it also divides R. And therefore, D is a common divisor of b and R. Right? So we started with D being a common divisor of a and b, and we showed that it is a divisor also of R, and hence it is a common divisor of b and R, which is what we've written here. And conversely, if D is a common divisor of b and R, then you can show by exactly the same reasoning, D is a common divisor of a and b. So I didn't really need this line. All I'm arguing is that the set of common divisors of A and B is exactly the same as the set of common divisors of B and R, and hence the greatest common divisor is also the same. If they have exactly the same set of common divisors, the greatest common divisor is also going to be the same. So that's it. It's a very, very simple proof. All right. So this has some natural corollary that suppose I have two integers A and B, again not both 0, then the GCD of this is equal to GCD of that, and similarly the GCD of this is also equal to GCD of that. So let me try to justify this one, and the other one is very similar. So for this equality, I think one can just write A is equal to B times 1 plus A minus B. So this is playing the role of R, this is playing the role of Q, and if you just use GCD A comma B is equal to GCD B comma R, you get exactly that thing. And similarly, you can justify that. All right, so lastly, let us discuss one problem. This appeared in IMO 1959. 1959 was the first ever, the first time IMO was ever conducted, and this is the first problem from it. So the first problem in the first ever IMO, it asks to show that if we have a positive integer n, then the GCD of these two numbers is equal to 1. So very simple, we just use these things repeatedly. So GCD of 21n plus 4, comma 14n plus 3 is equal to, we subtract, is equal to 21n plus 4 minus 14n plus 3, comma 14n plus 3 equals to GCD, this is 14n plus 3, is equal to 7n plus 1, comma 14n plus 3. And this time I'll subtract the first one from the second one. So we get that. I'm just using these things in whichever way suitable. So this is equal to 7n plus 1, comma 7n plus 2. And now we have two consecutive positive integers, and their GCD is of course 1. And if you don't want to use that fact separately, you can just again do one more time the subtraction business. So we get GCD 7n plus 1, comma 1. And of course this is GCD 1, no doubt about that. So very simple problem and a very neat solution to it. Yeah, and with that I want to end this lecture. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.